Hi everybody, we're going to quickly use Gauss's law to derive the field around a wire. Let's say we have an infinite wire of length L, so I'm going to draw the wire like this. And the wire is infinite, so it extends in both directions. And let's call the charge density of the wire lambda. Positive or negative, doesn't matter. And let's say we're interested in the electric field a distance r from the wire at a point. So to use Gauss, we can do this a number of ways. The easiest way is to do it using Gauss's law. And the first thing to notice is this wire has cylindrical symmetry, and so a cylinder is an excellent choice of a Gaussian surface. It's also important to note that the electric field of the wire is always perpendicular to the wire in all directions. I'm drawing just the ones in the plane of the diagram, but remember that if I was looking head on at the wire, that same field would be pointing radially outward from the wire. Okay, so let's draw our Gaussian surface surrounding this object. Our Gaussian surface is going to be a cylinder, so I'm going to draw a cylinder. And that cylinder is going to have length L and radius r. Now let's write Gauss's law, which is that the integral around a closed surface of E dot dA, which hopefully we don't have to truly evaluate, is equal to the enclosed charge over epsilon naught. First, let's evaluate the amount of charge enclosed by this Gaussian surface. Well, we know that an amount of length L is enclosed by the Gaussian surface, and so the Q within that, enclosed within that, is just going to be lambda times L. And so this side of the equation becomes lambda L over epsilon naught. Now remember, L was arbitrary, so hopefully the other side of this equation also contains an L, because it doesn't make any sense that this should depend on the length of our Gaussian surface. That length could actually be anything. So what we want to do now is evaluate this side. And so first of all, we can notice that the electric field anywhere along the cylindrical part of the Gaussian surface is perpendicular to the Gaussian surface and constant at that radius r. So if I take a radius r, if we come over to this picture, at every point along that radius, the electric field is perpendicular to the surface, and it also is the same value because of symmetry. The other thing to notice is on the end caps, the electric field is parallel to the surface, and you can see that right over here. I'll highlight it in red. The electric field is parallel to the surface, and therefore, even though the electric field exists on that surface, there is no flux because the dot product is 0. So let's fill it out. So this just becomes the electric field at a distance r times the surface area of the curved part of the cylinder. And just to remember your surface area equations, that's equal to 2 pi r times L. If you have a cylinder of length L and radius r, the surface area is 2 pi r, which is like one circular ring, and then multiplied by L for the entire height of the cylinder. And so now I have my E and D and A, and that's going to be equal to lambda L over epsilon naught. And you'll notice, as we expected, L is going to cancel. And I get E of R, E at a distance R, equals lambda over 2 pi epsilon naught R. And that is the electric field, a distance R, from an infinite wire.